Hi, honors chemistry students. It's Miss Becker. I thought I would make a video of the water solutions review that you guys uploaded. So hopefully you have already uploaded it to Canvas. And I'm going to post this video after the upload has been done. So I'm going to go through my answer key and maybe clarify a couple things. So you will see this populated underneath the PDF and also the Google Doc. And you will also see that I have posted, Miss G had her students populate a study guide, so you could have access to that as well. So if I go into my PDF here, and again, I'm just going to talk you through some of my answers so you could get some clarification. So we usually do this as a station review around the classroom. So I came up with a couple different things just to put a picture in the document. So first one is, and you could try this guys at home. You could take a paper clip and you could get it to float on water. So you could just take a glass of water. You could also do another experiment. You could overfill your glass of water if it's a pretty even lip on the cup. Because of water's high surface tension, you could get it to go over. You could overfill the container. That's very unique to water. So water has a very high surface tension. It has cohesion. You don't need to know that word. But because it has high surface tension, it has the ability to hold up, like you've seen in pictures, bugs and also a paper clip. You could also try to do this. There's many things online you could try to find a way to do this. But the big idea here is hydrogen bonding in water. So please be sure that you keep repeating that multiple times on this worksheet. Number two is, how do I know sodium chloride or any ionic solid is a electrolyte? Well, again, you've had some practice with the conductivity meter. So again, it was the battery with the light bulb on it. It has a positive and negative electrode. So essentially, if you have an ionic solution, the sodium or the cation is always going to go towards the negative electrode, and the chloride is going to go to the positive. Really, what you need to know is why it's an electrolyte is the fact that you have movement. Anytime you have movement of ions, movement of electrons, that is a conductivity, that is an electrolyte. So that's what you're getting at there. Number three, sodium phosphate, when it dissolves in water. Draw a diagram / draw an equation. What I want to see here is when you have an ionic salt, it breaks up into its ions. So this one, the reason I picked on this one was sodium. There's 3 of them, so I need to see a 3 in front of the Na+, and PO4 has a -3. And again, please go back to the back of your periodic tables. We have all of the polyatomics listed for you. So make sure you have that for the quiz when you take the quiz. And usually put water above the arrow. Again, that's not as important. But you should have any cation is surrounded by the oxygen end of the water molecule because oxygen is negative. Phosphate, that's the negative anion. It should have the hydrogen end of the water molecule focused towards it. And it is an electrolyte. Anytime you have charge, any ionic solid is going to be considered an electrolyte. Number 4, using a beaker versus a volumetric flask. A beaker is used to store chemicals, have a chemical reaction, pretty generic, but a volumetric flask is used to make a solution to exact molarity. And so again, in my previous videos and the other one, hopefully that you watched, it showed you a volumetric flask. They're used to make exact quantities. Number 5, this one, I didn't realize I had the wrong volume in there, but we'll just go with it. Anytime you're making a solution from a concentrated to a lower concentration, so this is starting at 18 going to 3.5, you're going to use M1V1. Is equal to M2V2. It doesn't matter how you set it up. It doesn't matter that the milliliters are there instead of liters. You could do it either way. It saves you the time and the mistake of converting to liters incorrectly. So you should have gotten 97.2 milliliters. Let's say you had a magical volumetric pipette. And so it transferred 97.2 exactly to a volumetric flask. You add water to the line on that flask, and you now have a 3.5 molar solution. So again, a VOL is volumetric pipette, VOL is volumetric flask. That is the two pieces of equipment that I do want you to know for the quiz. And please go back and watch those videos. The videos are making a solution are pretty good. Number 6, this is just a math calculation. I found the molar mass of sodium carbonate, and then I take the grams and convert that to moles. I change the milliliters to liters, and I get molarity. You guys usually have no problems with that. Number 7, acetone versus isopropyl. Please note that I will give you some of this, but you should be familiar with, again, alcohols have an OH on them. Exactly where that OH is not important. And then acetone, this came from the activity we did before we parted ways. Acetone does have a dipole because it has the C oxygen bond, so you're going to have some kind of dipole there. And then isopropyl alcohol, because you have an O attached to a hydrogen, again, is hydrogen bonding. Again, H dash bonding is going to be my abbreviation for hydrogen bonding. Isopropyl has hydrogen bonding, which is a stronger force than a dipole, is really going to be my answer for number 7. Number 8, 9, and 10 are some drawing ones. Again, NH3, please note that that is a dipole. It is polar. It dissolves in water. It's a non-electrolyte. The carbon molecules, again, you could draw C4H6 with a triple bond, or you could have 2 double bonds. It really does not matter for this exercise. It's the only force it really has is dispersion. There's really no dipole there. It's nonpolar. All carbon-hydrogen bonds are going to be considered nonpolar, and the molecules themselves are going to be linear or trigonoplanar or tetrahedral, so that is why they are always going to be nonpolar. It doesn't dissolve in water, carbon and hydrogen just doesn't, and we're going to consider them to be non-electrolytes. So that is why CH3OH, again, an OH bond is going to make it hydrogen bonding and going to make it polar because you have something weird attached to the carbon molecule. So anytime you have an unevenness or asymmetrical, it's going to be polar. It does dissolve in water. Alcohols do dissolve in water because it has hydrogen bonding. So water is what we call a universal solvent. So that's why it does dissolve it. But it is a non-electrolyte. So even though it does dissolve in water and is polar and has hydrogen bonding, it's still considered a non-electrolyte. So any carbon molecules, just put that in your notes, are going to be considered non-electrolytes. So 11, why ice floats. If you look up a diagram of ice, it comes into these hexagon shapes, and so that's what this model was trying to show you. And if we were in school, you would actually see a one up there. It does a much better job than my wonderful drawing here. You have oxygen and then you have hydrogens attached, and so each hydrogen is then linked to another oxygen on the neighboring water molecule. And again, please note this is always neighbor water molecules. So I have a gap or hole in the middle there. I can't get these water molecules any closer together. So that is why it is less dense. And thank God for that, because again, ice on water freezes on top, but doesn't freeze on the bottom. Otherwise, all of the fishies in the ocean would not be surviving after our long winters. Number 12, hydrogen bonding. Please note that most books do between 2 water molecules as a dotted line is hydrogen bonding, while the bond itself between oxygen and hydrogen is polar covalent. These are the 2 ones that you guys mix up quite a bit. So hydrogen bonding is between molecules. I want to call it a hydrogen force. I do know that most students get confused because it's called hydrogen bonding, but it's not a bond. It's just a force between 2 neighbor water molecules. So please, number 12, please make sure you understand that. 13, what I'm trying to show here with the molar mass is you have 2 water molecules attached. So you need to add the calcium, the sulfur, and the 4 oxygens, which I did here. And again, just to give you some more information, I have 2 water molecules. That dot means a plus sign. So 2 times 18, I add that, I get 172. So what I do is I set up my molarity is equal to X, which is my moles over my liters, and that gives me my moles. And then to find my grams, I apologize for the awful handwriting there. I should get around 301.3 grams, but because I only have 2 sig figs because of the 5.0, it should be 3.0 times 10 to the second grams. So that is why I have it listed that way. All right, number 14 and number 15. 14, I have a flask of water. I have a flask of isopropyl. Water is what we call a low vapor pressure, so you would not see much vapor above that water. Again, some water molecules have kinetic energy to go to the vapor phase. This is just evaporation, so note that water evaporates, so does all liquids. Isopropyl has a much higher vapor pressure because it's not as attached as the water molecules. Waters are really small. So in comparison to the isopropyl, they both have hydrogen bonding, but water being so small gives you the ability to lock them in closer together. So that is why it has what we call a low vapor pressure, and thank God for that, because otherwise we would not have water on the surface of our planet. So high vapor, lots of vapor above it; low vapor, very little. And finally, the last one is just a calculation. Only thing I want to add to this is probably going to be you're using an ionic solid, so you're going to mass out a certain quantity and add it to a volumetric flask. Again, think that we have every volumetric flask known to man. So let's say we have a 450 in the back. We're going to add that to the volumetric flask and add water to the line and mix. Again, look up at that solution video to kind of see how you use all of this.